For our pendulum, we used 3 pieces of 2x4 screwed together into a U shape and hung a weight from an eyelet at the top with fishing line. For our water device, we used a solo cup with a hole poked in it at the bottom. We used a very small hole as opposed to the very large hole we used in the beginning because we lost our water too quickly to perform any accurate measurements.
Galileo Galilei was born February 15th, 1564, and died January 8th, 1642. Galileo was an Italian astronomer, mathematician, physicist, philosopher, and professor who made pioneering observations of nature with long-lasting implications for the study of physics. He also constructed a telescope and supported the Copernican theory, which supports the sun-centered solar system. Galileo was also accused twice of heresy by the church for his beliefs and wrote a number of books on his ideas. Galileo's contribution to our understanding of the universe was significant, not only in his discoveries, but in the methods he developed and use of mathematics to prove them. He played a major role in the scientific revolution and deservedly earned the nickname the father of modern science. In July 1609, Galileo Galilei learned about a simple telescope built by Dutch eyeglass makers and soon developed one of his own. In August, he demonstrated it to some merchants who saw its potential, who saw its value for spotting ships, and gave Galileo a salary to manufacture several of them. Galileo continued to study mathematics after leaving university, supporting himself with a minor in teaching positions. During his time, he began his 2-decade study on objects in motion and published The Little Balance, describing the principles of weight, the principles of weighing small quantities, which brought him some fame. In 1602, Galileo began conducting experiments with pendulums in order to examine if their periods are indeed constant. So that's a brief introduction to what we're going to be talking about next, and that's going to be pendulums and if they do really stay in constant speed or have constant periods. And the backstory to that and how Galileo started thinking about this was when he was in a church cathedral, and he noticed a chandelier was swaying in the wind left and right, and he was curious to see how long it would take for it to go from left to right. So what he did was he grabbed his arm, took his pulse, and he counted how long it would take for it to go from left to right, and he did some mathematics and determined that it was indeed constant.
For the math for our pendulums, we have the sum of our time equals the length times the momentum about axis, which is I naught times alpha. Our negative omega sine theta times our length equals our mass times our length squared, d squared theta with respect to theta, our second derivative. Both of our masses are canceled, and we're left with d squared theta over dt, which equals negative g over L sine theta, which is our equation for motion. This is not a simple harmonic equation because it does not have the equation d squared theta over dt squared, which equals negative omega naught squared theta, or our second derivative. If we are working in rads, our sine theta equals theta minus theta cubed over the factorial of 3 plus theta to the 5th power over 5 factorial minus theta to the 7th power over 7 factorial, and so on to infinity. So our d squared theta over dt squared equals our negative g over L, or gravity over length, times our theta. After we let our theta naught square equal gravity over length, which is d squared theta over dt theta, which in turn equals our negative omega naught squared theta. This in turn will give our theta equaling our theta max times cosine of the square root of g over L, or gravity over length, times our t plus phi. Our second one is d theta over dt, which equals our angular velocity, and that's going to equal our negative omega times the square root of g over L, or gravity over length, and that's all multiplied by sine of the square root of g over L times t plus phi. After our frequency equals omega naught over 2 pi, which in turn is going to equal 1 over 2 pi times the square root of gravity over length. And after finding our frequency, our time is going to be 1 over our frequency, which equals 2 pi times the square root of L over G.
For our pendulum project, we did 2 different lengths of string and 5 tests for each length. We made sure to make the pendulum go through 10 complete cycles for each test run. For the first length of string, which is 16 1/8 of an inch, or equal to 0.41 meters, we got the first test run to equal 51.4 grams of water, second test run to be 50.0 grams of water, third test run to be 47.9 grams of water, fourth test run to be 46.8 grams of water, and fifth test run to be 46.8 grams of water. With these 5 numbers, we took the average weight, which was 45.58 grams. Then subtracted the weight of the empty cup, which is 12.8 grams, to get 35.78 grams. With this, we found the frequency to equal 0.7789 hertz, and the time to complete one cycle is 1.2838 seconds. For the second length of string, we used 7 3/4 of an inch, or equal to 0.197 meters. For the first test run, we got 36.4 grams of water. For the second test run, we got 37 grams of water. For the third test run, we got 36.4 grams of water. And for the fourth test run, we got 36.8 grams of water. For the fifth test run, we got 30 grams of water. With these five, we took the average to get 36.52 grams, subtracted the 12.58 for the empty cup, and got 23.82 grams. With this data, we got the frequency to equal 1.12354 hertz, and the time to complete one cycle was 0.89 seconds.